We, the second year students from the EXTC department of Sardar Patel Institute of Technology, Mumbai, have prepared a mini project on audio signal processing and filters. We have simulated this on VS Code using the Python programming language. Before we look at the simulation, let us look at some key concepts. The Fourier transform. The Fourier transform is a mathematical technique used to decompose the signal into its constituent frequencies. This transformation converts the signal from the time domain to the frequency domain, providing insight into the frequency components of the signal. The discrete Fourier transform, or the DFT, is the digital version of the Fourier transform, which is used to process signals that are sampled at discrete intervals, as is the case with digital audio. In the frequency domain, a signal is represented as a sum of sinusoidal waves, each with a certain frequency, amplitude, and phase. By modifying these frequency components, you can filter the signal in various ways. Now let us look at some basic filters. A low-pass filter. It allows frequencies below a specified cutoff frequency to pass through and attenuates higher frequencies. This is useful for removing high-frequency noise. A high-pass filter. It allows frequencies above a specified cutoff frequency to pass through and attenuates lower frequencies. This is often used to remove low-frequency noise such as hum or rumble. A band-pass filter. It allows a specific range of frequencies to pass through while attenuating frequencies outside that band. This is useful for isolating a particular frequency range, such as the human voice or any musical instrument. The band reject filter, also known as the notch filter. This filter removes frequencies within a specific range while allowing frequencies outside that range to pass. This is useful for removing unwanted interference or specific noise in signal. The filters are applied by manipulating the frequency domain representation of the signal after the discrete Fourier transform. Now, for the implementation of different types of filters in the frequency domain, the following steps are taken. For a low-pass filter, the frequency components with frequencies higher than the cutoff frequency are set to 0. This is done by checking the magnitude of each frequency component and setting those above the cutoff to 0. For a high-pass filter, the frequency components, frequencies lower than the cutoff frequency, are set to 0. This filters out low-frequency noise or any unwanted low-frequency components. For a band-pass filter, frequencies outside a specified range are set to 0. Only the frequencies in the range between the two cutoffs are allowed to pass through. For a band reject filter, frequencies within the specified range are set to 0. This removes a narrow band of frequencies while allowing all others to pass. Now let us look at the magnitude spectrum of the signal. Magnitude spectrum represents the amplitude of each frequency component in the signal. After applying a Fourier transform, you can calculate the magnitude of the frequency components. The magnitude spectrum is typically plotted for the visual inspection of the frequencies present in the signal. After applying these frequency domain filtering operations, the inverse discrete Fourier transform, or the IDFT, is performed to convert the filtered signal back to the time domain. The IDFT allows the manipulation of the time domain signal by reconstructing it from the filtered frequency components. The result is a modified time domain signal which corresponds to the audio signal after filtering. Since the DFT and IDFT are symmetric operations, applying DFT followed by filtering and then the IDFT reconstructs a time domain signal that is altered based on the filter type chosen.
Before the execution, let us first of all understand how the software part of our project is working. Our code consists of three parts. Let's examine them one by one. First of all, we have a file named extractaudio.py. What this file is doing is that it is converting all the data points from a WAV file into the form of a Python list so that it is easier for the code to process the data and calculate the required results. As we know that continuous audio does not exist in real life, all the audio signals are hence discrete time signals which consist of data points at various intervals of time. So what our code is doing, that it is extracting all the information from our wave file into the form of a Python list. Then we have a second file which helps convert the list of the extracted values back into the file. Why this is important can be seen in just a while. Let's see the third file. This is the most important part of our code and which is doing most of the computation required. So this file is combining the properties of both the other files and producing an output. As we can see in this line, we are saving the Fourier transform of our input audio signal into in the form of this list using the .fft, which is a built-in function in NumPy and which stands for the fast Fourier transform. It is a special type of more optimized function which can help calculate the Fourier transform in significantly less time. After that part, after we get the FFT result array which consists of the discrete time values of the Fourier transform, we can do various computations such as make a filter out of it. Here we have an if-else ladder which first of all takes an input from the user if the user wants to have a low pass, high pass, band pass or band reject filter. According to that, this part of code handles the fast Fourier transform and zeroes out the frequencies wherever required. For example, in the case of a low pass filter, as we will set the frequency to 2 kHz, this part of code will zero out all the frequency values to 0 which are less than 2 kHz in the Fourier transform. After this, we have to perform an inverse Fourier transform on the Fourier transform of the signal. It is done by this line, and again the .ifft function is a highly optimized function which is present in the NumPy library, which is responsible for calculating the inverse Fourier transform for our signal. We have also plotted the input signal, output signal and Fourier transform of our sound. And finally, this part of our code is saving the audio file in the specific location for us to hear. So that is the basic structure of our code. Let us begin with the execution of our project. As an input file, we have a file which consists of all frequencies from 0 Hz to 10 kHz. Let us have a look at the audio file first before we execute the code and listen to how it sounds. So here the input file is in the same directory as our code. Let's listen to it. So as we were able to see there, our input audio was a frequency sweep from 0 Hz to 10 kHz. Now let us perform operations on this audio using our code. So here we are in VS Code. Let's run the code. In the terminal, let's specify the plots. As our first example, we would consider a low pass filter for our sound. Let's set the pass frequency of the audio to 2 kHz, that is 2000 Hz. So here the plots are. Let's have a look at them one by one. Input audio. We can also zoom in onto this plot to see the individual frequencies of our sound. So here they are. As we can see, the frequency is steadily rising for our signal, which is kind of what we expect from the audio. Now, as we had set the pass frequency for our low pass filter to 2000 Hz, we can see that in the Fourier transform, all the elements after 2000 Hz are zeroed out. So this is a remaining Fourier transform for the signal. Now, after performing this inverse Fourier transform on this Fourier transform, we get an output signal. As we can see that somewhere after 2000 Hz, all the frequencies in the sound are zeroed out. So that was what we exactly wanted for our filter to perform. Now let's listen to the output audio. The output audio also gets saved in the same directory where we stored all the codes. Now let's listen to the audio. Now as we were able to see, all the frequencies which were after 2000 Hz were not audible to us. Let's listen to the audio again. So there the point was. After this point, the audio became kind of inaudible to us, which means that our low pass filter is working and it's cancelling out all the high frequencies of our signal. Now let us move on to our second application, which is the high pass filter. Let us move back to VS Code and run the file again on the same audio. We will specify the plots. We will select the filter type to be a high pass filter and the pass frequency again to 2000 Hz. So here the plots are. Let's again look at them one by one. The input plot was essentially the same which we saw in the last case, as we haven't changed the input audio. Let's keep that aside and have a look at the magnitude spectrum of our Fourier transform. As we can see that our signal consisted of frequencies from 0 Hz to 10 kHz, and after 2 kHz, which we can zoom in into again, we can see that all the frequencies after 2 kHz are present while those below 2 kHz are zeroed out by our code. Now taking the inverse Fourier transform from this Fourier transform, we get a new signal, and as expected in the frequency sweep from about 0 Hz to 2 kHz, we don't have any input audio present, or it's essentially zeroed out, and after which all the input audio signal is there. So let's listen to the output audio that this code has produced. So we kind of expected this from our code. As we can hear, the audio at this part of the file is not audible to us, while it gets audible somewhere around here, which is 2 kHz. Let's listen to the audio again. There it is. After this point, all the audio and the frequencies above it are audible to us. So this means that our high pass filter is working as intended. It is zeroing out all the frequency components that are less than 2 kHz and allowing all the others which are above 2 kHz. So that is our application for a high pass filter. Now let's move on to our application for band pass filters. We again move to VS Code and run the file again. We would again specify the plots. Now we will choose the filter to be a band pass filter. Let's specify the lower limit of our frequency to 2 kHz and the upper limit to 3 kHz. So here the plots are. We will ignore the first plot as it was the same signal which I showed earlier. So looking at the Fourier transform, we can see that our signal consisted of frequencies from 0 Hz to 10 kHz. But now our output signal is consisting of frequencies, those are only from 2 kHz to 3 kHz. So our code is allowing this band of frequencies to pass in the audio file. Looking at the filtered audio, we can see what is expected from this code. All the frequencies that are less than about 2 kHz are zeroed out, and those above 3 kHz are also zeroed out, and only the parts of the signal between 2 kHz and 3 kHz in the frequency sweep are audible to us. Now let us listen to the output audio which this code has produced. So as we are able to listen, our audio became audible somewhere around this point to this point, which consisted of frequencies from 2 kHz to 3 kHz. Let us listen to the audio again. So that is what we essentially expect from a band pass filter, and our code is successfully doing that. It is filtering out all the frequencies lower than 2 kHz and above 3 kHz and only allowing the frequencies which lie between these ranges to the user. Now let us look at a band reject filter. We again go to VS Code and run the project. We would specify the plots. We would specify a band reject filter. Let us again set the cutoff frequencies as our previous example, that was 2000 Hz and 3000 Hz. So our code has produced Looking at the Fourier transform of our signal, we can see that all the frequency components that lie between 2 kHz and 3 kHz have been zeroed out and all the other components are allowed in the code. After taking the inverse Fourier transform of this Fourier transform, we get an output signal which looks like this. All the frequencies belonging between 2 kHz and 3 kHz are kind of zeroed out also in this output audio, which is what we kind of expect from a band reject filter. Now let us listen to the audio which this filter has produced. The output audio is right here. Let's listen to it. So in the output audio, the sound got zeroed out somewhere over here, which was 2 kHz, and it was again audible somewhere after here, which was 3 kHz. Let's listen to the audio once again. Our code is doing exactly what we expect from it. Our code has zeroed out all the frequencies between 2 kHz and 3 kHz in the output audio file, and all the other frequencies are audible. Hence, this is our application for a band reject filter. As a concluding remark, we can say that our code is successfully implementing all the types of filters on an input audio. In the real world, the audio might not be as simple as how we demonstrated in this example. Real world audios such as sound, such as songs, etc. consists of various frequencies that last for various time periods, and the sounds are essentially more complex than a single sine wave which we had demonstrated in this example. Our example was an extremely basic example of what a sound consisting of various frequencies could be, which was easier to see for this example. The same code can also be used for any type of sound and filters. A real-world application of these types of filters for sound processing could be in songs. For example, if I have a song where I can hear a very high frequency which is kind of annoying to me, and what can I do to reduce that frequency to make that sound more pleasant to me? I can apply a low pass filter or a band pass filter on that particular frequency component which I don't need in my sound. I can either zero out that frequency component or reduce it to some value, and after taking the inverse Fourier transform of that modified Fourier transform, I can get a sound signal or a song which is more pleasant to hear. So that there is a simple application on a real world problem in the form of a mini project. I would like to extend my heartfelt thanks to our Professor Najib Ghatte for guiding us through this course with dedication and expertise. Their insights and teaching have greatly enriched our understanding on the subject, and I'm truly grateful for the knowledge and skills we have gained. Thank you to all the listeners. Please do leave a like if you liked the video, share, and also subscribe to our YouTube channel.